Welcome viewers. So far we have discussed about charge and its types, electrostatic force between charges, superposition principle, electric field lines, electric dipole, dipole moment, dipole field on axial line and equatorial plane of dipole, torque acting on dipole in uniform electric field, electric flux and Gauss's law and its applications. Now, let us assess our understanding of basic concepts of electrostatics and try to solve some problems. What is the relation between electric field at any point at a distance small r from the center on axial line and equatorial plane of a point electric dipole? Now, we know that electric field at any point on the axial line of electric dipole is given as 1 by 4 pi epsilon naught 2 p r upon r square minus a square whole square multiplied by p cap, and electric field at any point on equatorial plane of electric dipole is 1 by 4 pi epsilon naught p by r square plus a square raised to the power 3 by 2, and the direction is minus p cap. Now, if the dipole is a point dipole, and we know that for a point dipole, we can take r as very greater than a. That means a square can be neglected as compared to r square, and these two formulae will become electric field on axial line will become 1 by 4 pi epsilon naught 2 p by r cube multiplied by p cap, and electric field on equatorial line will become 1 by 4 pi epsilon naught p by r cube multiplied by minus p cap. If we just leave the direction of electric field, then and we just want to compare the magnitudes of electric field on axial line and equatorial plane, we can easily observe that the electric field on axial line is just twice the electric field on equatorial line. E axial is just double of electric field on E equatorial, that is E axial divided by E equatorial is equal to 2 by 1. Now, let us move on to another problem. Compare the electric field due to a point charge with electric field due to a point dipole. We know that electric field due to a point charge q at a distance r is given by the formula 1 by 4 pi epsilon naught q by r square multiplied by r cap, whereas the electric field due to a point dipole, whether you find it on axial line or you find it on equatorial line, electric field due to dipole is inversely proportional to r cube. So, you can easily observe that electric field due to a point charge, if we talk of point charge, electric field is inversely proportional to, for point charge electric field is inversely proportional to r square, whereas for a point dipole electric field is inversely proportional to r cube. Let us move on to another problem. The distance of the field point on the equatorial plane of a point electric dipole is halved. By what factor does the electric field due to the point dipole change? Now, we know that electric field due to a point dipole on equatorial line or axial line is inversely proportional to r cube. In given question, r changes to r by 2. The distance of the point is halved. So, if r changes to r by 2, you can clearly observe from this relation that if r changes to r by 2, then E, electric field due to point dipole, will become 8 times. It becomes r by 2 cube and it will become 8 times of the original electric field. Let us move on to another problem. We know that electric dipole placed in a uniform electric field experiences a torque, and this torque is given by P cross E, where symbols have usual meaning. Which pair of vectors are always perpendicular? Now, from the property of cross product, you know that the cross product of two vectors is another vector which is perpendicular to both the vectors. Now, because torque, this tau, torque is the cross product of P and E. So, this torque tau is perpendicular to P and torque tau is perpendicular to E as well. So, tau and P are perpendicular and tau and E are perpendicular. These are the two pairs of vectors which are always perpendicular. Show diagrammatically the orientation of a dipole in the field in which torque is maximum, and number 2, half the maximum value. We know that torque acting on electric dipole when it is placed in uniform electric field is tau is equal to Pe sin theta. Suppose this is your electric dipole and it is placed in a uniform electric field, making an angle theta with the direction of electric field. Now, you have to find the orientation of the dipole when the torque acting on it is maximum. So, this torque will be maximum if value of sin theta is maximum. So, torque will become equal to tau max if sin theta is maximum, and the maximum value of sin theta is 1, and which happens only when theta is 90 degree. Hence, the dipole will experience a maximum torque when it is placed perpendicular to electric field. So, you can show it diagrammatically like this. So, this should be the orientation of dipole for it to experience maximum torque, and the value of that maximum torque will become tau max will be P E multiplied by sin 90, that is 1. So, this will be the value of maximum torque on the dipole. Now, you have to find the orientation of dipole when the torque acting on it is half the maximum value. Let us see. If torque acting on the dipole is equal to half of the tau max, you know what is torque? Formula for torque is Pe sin theta, and you know what is maximum torque? Maximum torque is Pe. So, from here sin theta becomes 1 by 2, which happens when theta is 30 degree or pi by 6 radian. That means a dipole will experience a torque which is half the maximum value when dipole moment of the dipole makes 30 degree angle with the direction of electric field, and you can show it diagrammatically like this. Suppose this is the direction of electric field. So, dipole moment of dipole should make 30-degree angle with the direction of electric field. Suppose this is minus q, this is plus q, this is your dipole, and the direction of dipole moment is from negative charge to positive charge. This is the direction of P, this is the direction of E. So, this angle should be 30 degree. Let us solve another problem. Check that the given ratio is dimensionless. So, you are given a ratio, that is K E square M E M P. You have to check that this ratio is dimensionless or not. So, it is very simple. You just divide the numerator and denominator by r square. If we divide the numerator by r square and if we divide the denominator by r square, then we can easily observe that this is the formula of a charge q is placed at one of the corners of a cube of side small a. Find the flux through each face of the cube. So, in this problem you are given a cube like this. Let us suppose a charge small q is placed here at one of the corners of this cube and each side of this cube is A. Now, you have to find the flux through each face of this cube. To solve this problem, we can imagine some cubes around this cube in such a way that this charge comes in the center of a big cube. For that, we may draw cubes like this. Then you may draw a cube below this cube. So, we have placed 3 cubes 1, 2 and 3. Now, we can place 4 more cubes, 1 in front of this, 1 in front of this one and 1 in front of this one and 1 in front of this one. So, by placing 7 more cubes of this type, we can place this charge at the center of a big cube. Now, the big cube so formed will have, every cube have 6 faces. Now, every cube has 6 faces around it, and the big cube so formed will have 24 faces of this size. As you can see that one side is having 1, 2, 3 and 4 faces of this side. So, the big cube formed in such a way, by placing 8 cubes will have 24 faces of this size, and the total electric flux passing through that big cube which is formed will be, according to Gauss's law, that will be equal to amount of charge enclosed divided by epsilon naught. This is the total flux passing through the whole big cube, and amount of charge enclosed is the charge q divided by epsilon naught. Now, we have to find the flux through each face of this cube, and because big cube is having 24 such faces, so the flux through each face phi, you can call it so the flux through each face will be 1 by 24 times of q by epsilon naught. Let us solve another problem. A charge small q is placed at the center of a sphere of radius capital R. Suppose this is a sphere of radius capital R and a small charge small q is placed at the center of this sphere. How would the flux through the sphere change if the radius of the sphere is doubled? Now, you know that flux passing through this sphere according to Gauss's law is amount of charge enclosed divided by epsilon naught, and you can clearly observe that this flux does not depend upon the size of the sphere, or you can say the radius of the sphere. That means if the radius of the sphere is doubled, that means r changes to 2r. In that case also flux will remain same, phi will remain same, because flux passing through a surface does not depend upon the shape or size of the surface. It depends only on the amount of charge enclosed by the surface. Let us have another problem. A charge small q is placed at the center of a hemispherical bowl of a radius small r. Find the electric flux through the hemispherical bowl. Suppose we have a hemispherical bowl like this, and a charge small q is placed here at the center of this hemispherical bowl of radius small r. Now, we can imagine another hemispherical ball placed over it in such a way that this charge q comes in the center of the hemi. Now, we can place another hemispherical ball over it so that this charge q comes in the center of a sphere, and from Gauss's law we know that flux passing through a sphere is equal to amount of charge enclosed divided by epsilon naught. So, this is the flux passing through the total sphere, whole sphere. So, the flux passing through the hemispherical ball will be equal to the half of this. So, flux through hemispherical bowl is equal to half of q by epsilon naught. Let us have another problem. Equal charges capital Q each are placed at the center of a sphere of radius small r and cube of side small a respectively. Find the ratio of flux through sphere and square. So, we have a sphere of radius small r and a charge q is placed at its center. Then we have a cube of side a and a charge q is placed at the center of this cube also. So, the flux passing through this sphere will be according to Gauss's law it will be q enclosed divided by epsilon naught, and flux passing through the square, will also be q by epsilon naught, because flux does not depend upon the shape or size of the surface. Hence, the ratio of the flux through sphere and the ratio of the flux through square will be equal to 1:1. Ratio will be 1:1. Let us have another problem. What is the magnitude and direction of electric field at any point between two thin uniformly charged infinite plane sheets having equal and opposite charge densities plus sigma and minus sigma? So, we know that electric field due to a uniformly charged thin infinite sheet is equal to sigma by 2 epsilon naught, and it is always normal to the surface of the sheet. So, this is the electric field due to a thin infinite sheet of charge. Now, in question you are given two sheets. Now, in question you are given two sheets which are of equal and opposite charge density. Now, in question you are given two sheets which are of equal and opposite charge density. Suppose charge density on the sheet 1 is plus sigma and charge density on the sheet 2 is minus sigma. Now, you have to find the electric field at any point between these two sheets. So, suppose this is the point where we want to find out the electric field. Now, from symmetry and from the charge density, we know that electric field due to this sheet of positive charge density will be towards right, because charge is positive. So, electric field will be towards right and normal to the plane of this sheet, whereas electric field due to the sheet of negative charge density will be towards the negative charge. That means it will also be towards right and normal to the sheet. So, the electric field due to both the sheets will be towards right. Let us suppose right direction as the positive direction of x axis. So, electric field due to sheet 1 in vector form will be sigma by 2 epsilon naught I cap, and electric field due to sheet 2 will also be sigma by 2 epsilon naught I cap. So, according to superposition principle, the net electric field will be the vector sum of electric field due to two sheets, and it will become 2 sigma by 2 epsilon naught I cap, that is sigma by epsilon naught I cap. So, the magnitude of electric field at any point between these two sheets will be sigma by epsilon naught, and its direction will be towards right, that is from positive plate to negative plate, that is sheet with positive charge to sheet with negative charge. Let us see another problem. What is the difference between Cm and capital Cm? Cm and capital Cm. These two look same, but this Cm refers to centimeter, which is a unit of length in CGS system, whereas this capital C refers to coulomb. and M for meter. So this becomes Coulomb meter, and you know that Coulomb meter is the unit of electric dipole moment. So cm is centimeter, unit of length, and capital Cm is Coulomb meter, that is the unit of electric dipole moment. Now let us have another problem. What is the difference between, both are Coulomb, but do you find any difference between them? In this Coulomb, first letter is capital letter, and in this one first letter is small letter. So first letter is capital. So whenever first letter is capital, it refers to the name of a scientist. It is the name of a scientist, Coulomb, that is Charles Augustin de Coulomb, who gave Coulomb's law. And in this, because first letter is small, so this Coulomb is the unit of charge. It is unit of charge, and this is the name of a scientist. In this program, we have discussed some interesting problems related to the concepts we have learned so far. For better learning, for better clarification of concepts, try to solve more and more problems. Keep watching our videos to enjoy learning physics. Happy learning. Thank you.